As you guys can see from the title of the notes, we're going to be manipulating series. So let's start this off by reminding ourselves about the 4 special series that as a BC student we must know. And at the time that we were introduced to them, I didn't call them a Maclaurin series, but now I will. A Maclaurin series, as you may remember now from recently, Maclaurin series is just a power series that's centered at 0. And as you can tell from the 4 that we've worked with previously, the centers of all of these series are going to be 0. Well, at least when you show the expansion, you'll see that the center is 0. So I'm going to just go ahead and flash up the answers here. You might want to take the time to kind of self-test. What I mean is, do you remember what this power series looks like for e to the x? And if you do, try and crank it out here and expand a few terms. Okay, because that's something that you do want to commit to memory, and this is an opportunity to do that. All right, so maybe you might want to pause the video, try and crank it out on your own, see how well you did, and then we'll go from there. Okay, well, so they are. All right, just more memory space here. Hopefully you can get a handle on sine and cosine. I see that's pretty prevalent on the AP test. When you look at sine and cosine, just remember that a function and its power series representation must match at all points. So you probably likely see that the signs are alternating both on sine and cosine. Hopefully you can remember that the even exponents belong with cosine, the odd exponents on x belong with sine. But if you get kind of stuck there, just kind of think about this. Since all points must equal on the function and the power series representation, remember cosine starts at 0, 1, so that's going to kick off your series, 1. Whereas sine, if you think about it, it does cut through the origin. And so if you want to think about it in that, kind of light that, we're starting at 0, there is no constant term. We get right to the power functions, the variable, the x. All right, so hopefully you did okay. So let's look down here and see what we're doing today. We're working with these series. So these are given to us, and if we've memorized them, we can actually do things a lot quicker if we have them committed to memory. All right, so let's look at this one right here. Find a Maclaurin series for f of x equals sine x squared. Well, how do we do that? Well, we've got sine of x. Okay, so what we're going to do is we're just going to replace every x in the sine x series with x squared. It's just a shortcut to actually having to find the power series representation the long way. And the long way to find the power series representation for this function is to use the technique, an algorithm that we're going to learn when we cover Taylor series. All right, so for this, what might be best is for you to put right here front and center for yourself the sine series. And this allows you to keep writing it down. It allows you to kind of reinforce and memorize. Okay. Starts at x and alternates. And actually, I don't think the +1 is here. Well, I didn't do a good job. I get that confused sometimes with the 2n plus 1. Okay, so the directions say give the first 4 non-zero terms and the general term. So I actually, in Sine, which I'm going to be using to create this new series here, is I've got the first 4 terms, and then I have a representation of it here. All right, so now I'm going to come down here and say, okay, well, f of x here, this f of x that I want, you could have called this something else. If it made you feel better, you call it g, since f of x is going to be defined to be sine of x squared. Okay, everywhere I see x, I'm going to replace it with x squared. It's like a composition. So we're doing that for the first 4 non-zero terms in the general term. Everywhere you see x, replace it with x squared. I don't know if that disappeared up there. I'm going to leave it just like that. There's no indication to clean up. There's no reason to clean up. Okay, so for this x, it becomes x squared. Going back and filling in my x squareds. Do you have to clean up if you want to? I think you just lose the pattern. We're done. Let's move on. Let's manipulate sine again, but this time replace every x with 3x. So because these problems are back to back and I have the parent series, so to speak, right up here, I'm not going to rewrite it. All right, so everywhere I see x, I'm going to replace it with 3x, which is just the function I'm trying to find a series for. All right. Okay, everywhere I see x, replace it with 3x. You could either generate a few terms by going through n equals 0, etc., or you can just go simply up here to the parent series, and everywhere you see x, replace it with 3x. You can clean it up if you want, but I think we're done. All right, so on the back, we're asked to find the 6th degree Maclaurin polynomial for this function here. Well, obviously, I'm going to manipulate the cosine parent series, so I'm going to write that down. Or maybe not, I don't know. Don't act up. All right. All right, if things disappear, you guys have the parent series on the other side. All right, this is cosine. It's going to start at 1. It's going to alternate with the even powers. Okay, let's see now. It asks me to find the 6th degree Maclaurin polynomial. So 6th degree, I need to go to the highest exponent of 6. But I don't know what that means as far as this is concerned. I'm just going to expand this out a few terms here. And if I need more, I see the pattern. Okay, I can get more. All right. So f of x. So everywhere I see x, I'm going to replace it with square root of x. So actually, I didn't even need this nth term here. For the directions, I just need the 6-degree Maclaurin polynomial. Oh, and that's important too, a polynomial. I don't want a series, I just want a 6-degree. So this nth term really isn't going to have a bearing on what I need for the requested information here. So, all right, everywhere I see x, I'm going to replace it with square root of x. So, all right, I've got 1 minus. Remember, this is going to be squared, but I'm going to dump in a square root of x. Ooh. Okay, so that's going to become an x, a linear. Wow, this is going to be pretty involved. Plus, I'm going to write skinnier. If I put in a square root of x here, the square root of x to the 4th power is x squared. I'm only up to a 2nd degree polynomial. Polynomial means it ends, it's finite, it's not an infinite series. I need to get to the high exponent of x to the 6th. So it appears that I'm going to have to go to x to the 12th, because when I square root, that's taking half the power. That's just the cube. That's a 3rd degree polynomial. And again, remember, Maclaurin just means a center of 0. Polynomial means it ends. Okay. The parent series suggests I have all even exponents, so I'll just carry this out a little bit further. I guess it could have been worse. Okay, notice I didn't do a dot, dot, dot. Okay, I'm finished here. I probably should do some cleanup to really indicate that this is a 6-degree polynomial. Okay, but I think for our purposes, we're just going to stop here. All right, use a power series representation to find the integral of cosine square root of x. Ah, yeah, great example here. You know, we can't find an antiderivative for this. We couldn't integrate this. We don't have any technique to do that, though. Well, this year, anyway. U substitution would fail. It's not an inverse trig integral. Nothing we've learned in BC Cal is going to help us find this antiderivative other than knowing that we can integrate the terms of a power series. So pretty interesting. Yeah, let's replace cosine squared of x with a few terms and integrate it. Okay, so from the previous example, I know what a few of these terms are. Now, here I'm going to clean up what I had previously, because my objective here is to integrate. Now, who wants to deal with those square roots? So this is x squared over 4 factorial. All right, it wasn't, real explicit as far as the number of terms, okay, to find. So I'm just going to get enough terms here so I can kind of, see a pattern. All right, plus, oh my goodness, dot, dot, dot. All right, and I will use the nth term of the cosine series, so that's going to be -1 to the n. Everywhere I see x, I'm going to replace it with the square root of x and take it to the 2n power. All over 2n factorial, yeah, plus dot, dot, dot. All right, and this is really a dx here at the end. All right, so we have some integration to do. Antiderivative, reverse power rule, 2 times 2 factorial, increase to 3, divide by 3, multiply by the 4 factorial that was there, minus x to the 4th divided by 4 times 6 factorial, plus this should be x to the 5th divided by, I'm assuming 5 times the next even number is 8 factorial. This is ridiculous. And let's integrate this nth term with respect to x. Okay, I probably should have cleaned this up here. Okay, you can always square the square root of x, and so that will take care of simplifying. This is really just x to the n. So the square of the square root is just x, x to the n. Okay, so that makes it easier to integrate, which is our objective here. I'm going to raise n to the, n plus 1? And then also divide by n plus 1. And as you can see from each of these individual terms, that really fits that description right there. Well, sort of. Plus dot, dot, dot. So did we find a power representation, a power series representation for the integral cosine x dx? Yeah. We inserted a few of the terms of that power series, and then we integrated each of them. Okay, so another way to do this actually is just kind of collapse it if you wanted to. And don't forget the constant of integration like I always seem to do. I'll put it first. If you wanted to collapse this, you don't have to unless requested. You can just write the nth term here. Maybe that'll stay. No, but it might come back. We'll take a look at this bottom one in the next video.